Okay, so we ended the lecture last time by discussing several key system properties, things like stability, causality, time invariance, and linearity. And we're going to sort of follow up on that today by talking about the system responses when we have linear and time invariant systems, okay? And so let's just be more formal about this. And so what we're going to do today is we're going to look at system responses for so-called LTI systems. Okay? And so LTI systems are systems that are simultaneously linear, that's the L is, and time invariant, that's the TI. Okay, so systems that have both these properties, sort of linearity and time invariant. And so why are we focusing on these systems? And so it's not because that in general physiologic systems sort of always are linear and time invariant, or even that a majority of physiologic systems are truly linear and time invariant. Rather, we focus on these systems because when a system is both linear and time invariant, there's a certain sort of kind of regularity or consistency that's possible in the analysis, such that we can systematically determine the response with sort of methods that are extremely powerful. And it turns out that even though physiologic systems generally aren't sort of entirely linear or time invariant, that we can often sort of model these systems, at least in certain sort of relevant regimes, such that the linear time invariant systems provide a pretty good approximation, a really useful approximation. Okay, so in short, these systems sort of are amenable to sort of rigorous analysis, and they can provide good approximations to sort of real kind of biological, physiological phenomena. All right. And so what's so good about these linear time invariant systems sort of in particular? And so the specific thing that we're going to be focusing on today is that these linear and time invariant systems have the property that if we that the responses to in some sense, the most basic input, something that we're going to call a unit impulse function input, okay, is going to determine the response to any possible input. Okay, and it's really sort of a powerful thing. But if we know the response to some basic input, then we can use that to figure out the response to any possible input. Okay, so first of all, what's this unit impulse function? And so the unit impulse function. So we're going to call this is input. So when this is the input, then the input x of n is going to be equal to delta of n. Okay, and so delta of n is going to what we're going to use to refer to a unit impulse function. It's so important that we sort of assign our own sort of character to it. It's Greek letter delta. Okay, and so we use n for discrete time, and analogously t for continuous time. So if it's a continuous time system, we'd write x of t would be equal to delta of t. Okay, so x of t and x of n refer to the input. Okay, and this delta of n and delta of t are in this particular case of the input being a unit impulse function. Okay, and so in a discrete case, a unit impulse function looks like this. Okay, so if I'm making a plot of, say, delta of n versus n, this unit impulse function has a value of 0 for almost all values of n, okay? But it has a value, it gets a value of 1 when n is equal to 0, okay, and at no other times. Okay, so even though I'm drawing this function in some sense as a continuous function, delta of n is discrete, and I just draw it this way because it's sort of easy for me to draw. And so the values of delta n takes on sort of this value sort of at 0, and then there's a value of delta, so, and this value is 1, like I've written over here. Okay, and there's another value of this function at n equals 1, or n equals 2, n equals 3, n equals 4, etc. Okay, but these values, when n does not equal 0, it's 1, 2, 3, and 4 are all exactly 0, right? Analogously, when n is equal to minus 1, minus 2, minus 3, minus 4, etc., delta of n is also equal to 0. Okay, so this is the unit impulse function, and in some sense we can think of it as sort of the most sort of basic sort of input, that it's 0 at all times except the current time. Okay, and there's a continuous analog. We're not going to talk about that right now. We'll give examples in discrete time, and then we'll come back around to how this sort of translates into continuous time. Okay, just for the ease of explanation. All right, and so this response to a unit impulse function is so important that we'll give it its a special letter as well. Okay, and so this response is in general the response of a system we call y of t or y of n, and the response to specifically to a unit impulse function we'll actually call h of n. Okay, so remember our basic sort of diagram of system input-output relationships is that we have an input x of n or x of t, and that goes into some system. I just call it sys here. Okay, and that gives you an output y of n or y of t. Okay, depending on whether the system is discrete, like x of n, or continuous, like when the input is x of t. Okay, and in particular, when the input is, so that this is the general case. Okay, and then this for specific case, when x of n is equal to h of n. Sorry, I said that wrong. If x of n, in the specific case, when we have that the input x of n is equal to delta of n, okay, then the response y of n will be equal to h of n. Okay, and so h of n is the so-called impulse response of the system. Okay, and by that we mean is that's the system's response when the input is equal to a unit impulse. All right. Because the response of the unit impulse of a system to a unit impulse function determines any possible input, we can actually sort of think of the system as being characterized by this response. Okay, and so we're then often going to sort of in some sense or think of systems, right, in terms of their impulse responses. And so we'll often actually just go kind of whole hog and say that x of n is going to go into a system that is described by a unit impulse response of h of n and give us an output y of n, right? And so the idea is that what the system is doing, since it's completely described by the unit impulse function, we can actually sort of think of the system in some sense as a system that has a unit impulse response h of n. Okay, and we'll sort of think of the system this way. Okay. Now, for example, we will I'll draw just some arbitrary x of n. Okay, and let's make it look like, I don't know, this. Okay, so for this x of n, we'll give it a value of 2 at time equals 0, and a value of 4 at time equals 1, and a value of 1 at time equals 2. Okay, and then at times 3, 4, 5, etc., the values or the value of this function is going to be 0. Okay, and similarly at time -1, -2, -3, -4, etc., the value is also going to be 0. Okay, and so if we want to really be sort of really clear about diagramming this, we could put sort of this is a value x of n is value 0 here, a value of 2, and up here a value of 4. Okay, all right. And so the observation that we're going to make, that's really sort of the cornerstone of the whole sort of analysis that we're going to proceed with today and make use of for a good fraction of the semester, is that even when x of n isn't a unit impulse and doesn't actually particularly look super close to a unit impulse function, that we can break it down into into the summation of several scaled and shifted unit impulse functions. Okay, and so what do I mean by that? What I mean here is that we can take this x of n and we can express it as a sum, in this particular example, a sum of 3 components: x0 of n, x1 of n, and x2 of n. Okay, where x0 of n is just the part of x of n that that occurs at time 0. Okay, and so if I was to plot this, it would just look like this. Okay, so at time 0, x0 of n would have a value of 2, and at all other times it would have values of 0. Okay, and analogously, x1 of n, okay, would take on a value of 4 when x is equal to 1, okay, and be 0 at all other times. Okay, and finally, x2 of n would take on a value of 1 when t is equal when n is equal to 2. So this is n plotted, of course, over here on the x-axis. And so at n equals 2, it would be a value of 1. Okay, and 0 at all other times. So in these plots, this is 0 here, sort of the spaceline. Okay, and so we can take this x of n that has values at several different non-zero values at several different time points, and then break it down into the sum of components that has a value that each of which have a value only at a single time point. Okay, and these are just sort of shifted versions of one another, and what they and more generally, with these functions x0 of n, x1 of n, and x2 of n are scaled and shifted versions of this unit impulse. Okay, and so in particular, x0 of n is just simply equal to 2 times delta of n, right? And x1 of n it's 4 times a unit impulse that's shifted by 1 unit. Let me just write 1 here, 2 here. Okay, and so I could write this is equal to 4 times a unit impulse that's shifted 1 to the right. So that would be 4 times delta of n minus 1. Okay, and x2 of n would be equal to analogously 1 multiplied by delta of n minus 2. Okay. Okay, so now that we have this x of n broken down in this way, right, into as a sum of scaled and shifted impulse functions, right, then we can make use of the properties of linearity and time invariance to determine what the response is. Okay, and so remember that linearity has sort of two tenets, if you want to call it that. And the first is that if you were to break down some function into the sum of multiple components, then the response to that input function would simply be the sum of the responses that you would get for the individual components. Okay, and the second sort of tenet of a linear system is that if you take a scaled value, a scaled version of a function, then as an input, then the output is simply going to be a scaled version of the response to that input, where the scaling between input and output are the same. Okay, and so since we know in some sense what the since we know in some sense what the output is for delta of n, then we know because of linearity what the output is going to be for 2 times delta of n. Okay, so so the output for delta of n is going to be h of n, right? And so I'm just going to draw an example of what h of n could look like. And so here's h of n. And so in our example, we'll make h of n equal to, let's just make it this sort of staircase function here. Okay, so h of n will be 0 for all times less than 0, and then at time point 0 it'll have a value of 3, at time point 1 it'll have a value of 2, at time point 2 it'll have a value of 1, and then it'll be 0 for all times greater than 2, so time point 3, 4, 5, etc. And similarly, it'll be a value of 0 at time -1, -2, -3, -4, etc. Okay? And so if x0 of n is simply equal to 2 times delta of n, right, then the corresponding output that comes from x0 of n, which we'll call y0 of n, okay, would simply look like 2 times h of n, right? And so it would look like the following. Okay, where y0 of n is 0 for all times less than 0, and then at time 0 it's going to value 6, which is 2 times h of n, and then it's going to have a value of 4 at n equals 1, and a value of 2 at n equals 2, and a value of 0 for all values of n greater than 2. Okay, and so I could just sort of write this to be sort of clear. Y0 of n is simply equal to 2 times h of n, right? Because x0 of n is equal to 2 times delta of n, y0 of n is equal to 2 times h of n. Okay, now we can play this sort of same game to figure out what y1 of n and y2 of n are. Okay, these are the outputs corresponding to x1 of n and x2 of n. Okay, and so y1 of n, okay, is going to be equal to 4 times h of n minus 1. Okay, and so this this next sort of part is this is where time invariance comes into play. Okay, and so the idea behind time invariance is if we know what the output to a system, we know what the output is for a system with some particular input, then if we time shift that input, right, so we know what the output is for delta of n here, if we time shift that, so delta of n minus 1 is a time shifted version of delta of n, it's just shifted in time forward by one unit of time, then the output is similarly going to just be time shifted by that same amount. Okay, and so here what we have is 4 times multiplied by delta of n. Okay, and so what we're going to have for the output y1 of n is going to be some system response. Let me give myself a little more room to write this one. Let's multiply by 4. It's a little bigger. Okay. Okay, so what we have is 4 times this h of n, but time shifted by 1 unit. Okay, and so that's going to look something like this. Okay, where at time 0 we're going to have a 0 output, but starting at time 1 we're going to have an output and then that steps down thereafter. Okay, and the values of the output at time 1 is going to be 4 times what this peak impulse response is, and so that will be 4 times 3 is 12. Okay, and leave myself too much room here. We'll just draw this over here. Okay, and then this at the second step it's going to be 8, and that's going to occur at time step 2, and then the last step is going to be 4. That's going to occur at time step 3. Okay. All right, and then finally, just to sort of completely reinforce this, y2 of n is going to be equal to 1 times h of n minus 2. All right, and so it's because the output here is just 1, we don't actually have to scale the response of the impulse response function. We're scaling it by 1, which of course is not scaling at all, but we are going to shift it by 2 units. And so instead of 3, 2, 1 beginning at time step 0, what we're going to have is a response that's 3, 2, 1, but beginning at time step 2. Okay, and so we start at time step 2, 3, and 4. And time step 1, time step 0 are going to have values for the output that are equal to 0. Okay, so just super clear here. This is with a 0 point on these axes. Okay, and so what linearity says, right? The main thing linearity says is that if we know what the outputs are to these various sort of sub-inputs that sum into x of n, then all we need to do is to take these outputs and sum them, and that will give us what y of n is. Okay, so y of n is basically this summation here, okay, of these. So if we just take this and this and this and sort of add them, right, at each time point. All right. So I'll just show the result up here. Okay, and so what we have is that, well, at time point 0, then we're going to get y0 is equal to 6, y1 is equal to 0, and y2 is equal to 0. So the output yn at time point 0 is going to be equal to 6. 6 plus 0 plus 0 is 6. Okay, so before time point 0, it's going to be 0, and then it's going to be 6 at time point 0. At time point 1, what we can do is we can add y0 of 1, which is 4, plus y1 of 1, which is equal to 12, plus y2 of 1, which is going to be equal to 0. And so we get 4 plus 12 is 16. Okay, at time point 1, and then at time point 2, we get y0 of 2, which is 2, plus y1 of 2, which is 8, plus y2 of 2, which is 3. And 2 plus 8 plus 3 is, of course, 13. So the output is equal to 13. Okay. And then finally, at time point, that's at time point 2. Okay. And finally, at time point 3, y0 of 3 is equal to 0, plus y1 of 3 is which is 4, plus y2 of 3, which is that right? Yeah. Plus y2 of 3, which is 2. And so 0 plus 4 plus 2 is 6. Again. Okay. And then, sorry, I said finally, but that's not the final one. And the final one that we'll have to deal with will be at time step 3. Sorry, it will be at time step 4, where y0 of 4 is equal to 0, y1 of 4 is equal to 0, and y2 of 4 is equal to 1. So 0 plus 1 is 1. Okay, and after time step 4, right, y of n is equal to 0 because all of these functions y0, y1, y2 are 0 when you have when you're at n is of 5 or greater. Okay, and so here we sort of we have the solution for this particular example. All right, but we'd like to and so it'd be good to sort of step back and sort of take a look at what we've done here, just as sort of a reminder, right? And so we had some x of n, which is not anything close to a unit impulse function, right? So it has values at multiple time points, not rather than just a single time point. But we can sort of break it up into the sum of scaled, so the scalings of these sort of things are 2, 4, and 1, and shifted impulse functions, right? And so the shift of the x0 value is going to be 0, but the shift of the x1 value in terms of representation by a unit impulse is going to be shifted by 1, and then the x of 2, the n of 2 value is going to be shifted by 2, right? And so if we take those scaled and shifted sort of components of the input, we can find the responses to each of those components, right? And these will be, again, scaled and shifted versions of the impulse response function, h of n, right? So you can see this first one is going to be scaled by a factor of 2 and shifted by 0. Second one is scaled by a factor of 4 and shifted by 1 to the right. And the third one is scaled by 1, which really isn't scaled at all because the input here is just of size 1, but shifted over by 2 units because that input is occurring at time n equals 2. Okay, and then once we have what the responses are for each of these inputs, we can simply add them up to get what the sort of the overall sort of composite output is, y of n. Okay, plotted here against n. All right, so if we wanted to think of this sort of a little bit more systematically, sort of figure out, like, how did we get this without sort of thinking about it so graphically, it would be good to sort of give an example. And so one example I could give is, well, what exactly did we do if you want to sort of trace it back a little more to come up with y of 2, okay? And so we got y of 2 is equal to 13 by summing 2 plus 8 plus 3. But how did we come up with the 2, 8, and 3, right? So this 2, right, the first thing that we're summing to get y of 2 was equal to the h of 2, which is 1, multiplied by x of 2, which is 2, right? So we had, right? And so what we have here is that y of 2 is equal to be, the first term in it is x of 0, which is equal to 2, multiplied by h of 2, okay? And then the second thing we're going to add in is the 8. But where does that 8 come from? Well, the 8 comes from the second step in this impulse response function, which is h of 1, okay, multiplied by x of 1. Okay, so x of 1 multiplied by h of 1, okay? And then the third thing that we're going to add to that is this value of 3, and this 3 is comes from x of 2, right? Multiplied by h of 0. Okay, so it's the first step of the in this impulse response, which is h of 0, and then multiplied by the scaling of the input at time 2, which is x of 2, which just happens to be 1 here, so things aren't actually scaled. All right, and so we can just sort of look at the pattern here, and what we're doing is we're stepping through the input x, right, the time 0, time 1, and time 2, and as we're stepping through this input, what we're doing is we're stepping through, in some sense, in a backwards direction through the impulse response function, getting h of 2, h of 1, and h of 0. Okay, and so this is sort of, and so we can sort of write this sort of in general as y of n, okay, is going to be equal to the input at some time k multiplied by the impulse response function at time n minus k. Okay, and we're going to sum this up over all k. Okay, and so another way to write this one more generally is that y of n is equal to the sum from k equals, in the most general way, would be minus infinity to infinity, like all, right, all possible values of x of k, right, multiplied by h of n minus k. All right, and so where does this come from, and what does this actually mean, right? So you can sort of think back here that this y of 2 comes from taking the input x at time 0, right, and multiplying it by h of 2. So what is h of 2? H of 2 is the response to to the unit input two time steps after that input occurred, right? So remember, the unit input delta of n occurs only at time step, as a non-zero value only at time step 0, okay? And the response to it 2 time steps later is what we call h of 2, all right? So y of 2 is going to be x at whatever x occurs at time step 0 plus the response 2 time steps later, right? And then we're going to, multiplied by the response 2 time steps later, plus the value of the input that occurs at time step 1, right, times the response to that would occur 1 time step later, right, which would give you time step 2, plus the response, plus the input that occurs at time 2, plus the immediate response to that input, all right? So in this sort of general case, what we have is that y at the output at some time step n is going to be the input, right, at some other time step multiplied by the impulse response function, right, at a lag that's equal to the difference between n and k, right? So if x is at happening at time k, what we're going to do is we're going to look at what the response is at time n. The impulse response is at time n minus k, which is the lag that would that you would need to go from time step k 2 times step n. All right, and so this is the general formula for what the response is going to look like, and this general formula, we have a name for it, and we call it the convolution sum, or summation. Okay, and so this convolution summation is so important that we actually give it sort of its own sort of expression. Okay, and so in general, what it says is that this output y of n is equal to this sum, convolution sum of x of k and h of n minus k. And we can actually sort of write this in a sort of special nomenclature. I'll write it up here as that y of n is equal to x of n convolved with h of n. Okay, and the shorthand version of that would be just y is equal to x convolved with h, where it's assumed that y, x, and h are all functions of n. Okay, now it turns out that convolution is commutative. So if y is equal to x convolved with h, it's going to also be equal to h convolved with x. It doesn't really matter what the orders of these are. And so this summation here, summation of x of k times h of n minus k, is also equal to the commutative version of this, which is the summation k is equal to minus infinity to infinity of x of n minus k times h of k. Okay, just to be sort of complete, that's equal to the original way we wrote it, the summation of x of k times h of n minus k due to the commutativity. Okay, so these are both versions of the convolution sum. All right, and they can be sort of written as an operation: y is equal to x convolved with h, or y is equal to h convolved with x. Okay, and so going back to our sort of a way of sort of writing the system where x of n is going to some system that can be described by h of n to give you an output y of n. What we have is that this y of n is equal to x of n convolved with h of n. Okay, so viewed in this way, it's actually really simple, right? So if we have an input x and we have a system that has impulse response h, the output y is simply equal to x convolved with h, okay, or h convolved with x. That's it's commutative, it's sort of the same thing, right? And that's how you get the output, okay? And this is output. The specific convolution operation is described by this summation here, or this other version of it, which was just switched around in some sense. Okay, all right. We're going to stop there. Thanks.